In this chapter, we're going to continue on the story of thermochemistry and expand it into thermodynamics. So, first we need to refresh ourselves about what we know about energy. That is, energy is the natural movement of potential from one area to another. And on its own, nature dictates that energy must move from areas of high energy, such as the top of the waterfall, to areas of low energy at the bottom. This is done without any effort on our part. That is, the universe takes care of that. And towards the end of the chapter, we're going to be talking quite a bit about what the universe dictates must happen for a chemical reaction. Now, if we want to put this in terms of why molecules form, well, let's consider we have two hydrogen atoms here. And these two hydrogen atoms wander around until they finally begin to see each other and become attracted. That is, the electrons in the outer shell of the hydrogen atom begins to see the nucleus of the adjacent atom, and the result is the two atoms come together. They form a bond. They form a covalent bond, which results in a lowering of energy for those two atoms. And so the degree in which the bond forms, or the amount of energy that is released, is dependent upon the nucleus and the distance they are separated by. But the formation of a bond is always an exothermic process, meaning that energy is released. Well, when we talk about endothermic and exothermic processes, what we're really talking about is enthalpy. Enthalpy is a measurement of the difference in energetic states before and after a reaction has occurred, provided that we're at constant pressure. We can modify enthalpy to include changes in pressure, but that's beyond the scope of this course. Now, one thing you should recall or be aware of is that enthalpy is a state function, meaning that it is simply a difference between the beginning state and ending state, and doesn't include anything that happens during the course of the reaction, that is, energy barriers which have to be overcome. It is simply a difference of where you begin and where you end. You've been doing state functions your whole life when you've done subtraction. So imagine we have two paths for hikers going up a hill. We have the direct approach and the scenic approach. And both paths have different lengths to them. Regardless of which path you take, though, it doesn't change the elevation from the bottom of the path to the top of the path. That is, the distance from here, that is the difference from point right here up to the top of the mountain, is always the same. It's path independent. That's what a state function is. It's simply a difference of 2 points and ignores everything else that happens during or between those 2 points as we're performing a reaction. As you may recall, reactions can be exothermic, that is, they release energy. When you have an exothermic reaction, recall delta H is negative. And we can have an endothermic reaction, where delta H is positive. We end in a higher energetic state. What prompts us to examine thermodynamics is that there are reactions where endothermic processes are spontaneous, even though we wouldn't expect them to be, because energy naturally flows from regions of high to low and not from low to high. So there must be something else occurring during the course of a chemical reaction which allows us to overcome this heat issue. Regardless of whether a reaction is endothermic or exothermic, enthalpy cannot be used to predict whether or not a reaction should occur. Rather, we must begin to investigate a second component known as entropy, which will be the focus of the next video.